Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Welcome. This is Mr. Simon, and we are here to change our world with chemistry. We are still talking about alkanes, and our lesson today is physical properties of alkanes. Thank you for tuning in, and hope you are doing well. So, we are going to talk about physical properties today. But last time, there are some things we are talking about. We are trying to talk about the preparation of alkanes, the different methods of preparation of alkanes. So there are some things we are not covered. So we are going to just pass through them very quickly, very quickly. But before we pass through them, let's just write down some few equations of what we covered last time. So we looked at 4 methods of preparation of alkanes. So like for example, method number 1, we had A, B, C, and what? And D. So the first one was about the carboxylation, where we had left you with some work to do. We had something like this, CH2, CO. So in chemistry, we can also write like this. We can put our reactants here. Sodium hydroxide and the calcium oxide and what? Heat. So when it takes place, we get our alkane, which is the propane plus sodium what? Carbonate plus what? Water. Sodium carbonate, there is A here, plus water. Then the second reaction was about reduction. About what? Reduction. We can just give an example different from the one I gave you, but let's just revise through. In the presence of hydrogen and the platinum, so we get our alkane. Then we had also again reduction of alkali halides, where we can have this one plus what? Hydrogen, again in presence of platinum or in presence of sodium and ethanol. So we get our alkane again and HBr. We also had Wurtz reaction. I remember I had left you something like this, similar to this one. Is it like this? Is secondary alcohol? Let's just use this one. It's secondary actually. So we can do like this. We put 2 in presence of what? Sodium. It's somewhat different from the one I left you with, but just an illustration. So we also had, we said it will multiply by 2. So we have CH3, then we have CH what? 3, CH what? 3. So here you recognize you have 1, 2, 3 times 2. 1, 2, 3, 4, 5, 6, plus 2 sodium bromide. So this is just to pass through what we did last time. So we want also to talk about 2 other methods. 2 other what? Methods. One is using Grignard's reagent. Grignard's reagent is a reagent obtained from the reaction between, again, alkali halides. Remember the functional group for alkali halides? So this will be Grignard's what? Reagent. So this Grignard's reagent is unstable in the presence of even water vapor. In the presence of even water what? Vapor. It will change to alkane. That's why it is stored under ether. So we have this one plus magnesium hydroxide iodide. We can give another example. Here we have CH3, CH2, magnesium. This is also Grignard's reagent. In small amount of water, it will quickly form an alkane. So meaning water will donate 1 hydrogen to form 3. Then we have magnesium hydroxide. Then we have also bromide. So this is what we have here. on our screen. So is another method of preparation of alkanes. Then we also have another one. We are going to call it Clemensene reduction. Here we reduce carbonyl what? Compounds. Again, in presence of hydrogen. Presence of what? Hydrogen. But this time, this hydrogen is produced by zinc mercury amalgama in presence of hydrochloric what? Acid. So it produces hydrogen, which will reduce our carbonyl compounds to alkanes. So we can take an example here on F. Simple illustration where we have CH3. So here I've drawn my organic compound very well. So this hydrogen comes from a mixture of zinc, mercury amalgam, and HCl, which will produce these hydrogens. These hydrogens will come and reduce the alkane. So it will replace those two hydrogen what? Atoms here. Two hydrogen what? Atoms. So actually it replaces these bonds here. Actually to replace oxygen. So one of the bond here will combine with hydrogen, and another bond will combine with what? Hydrogen. So we shall have CH3, CH what? 3 plus what? Water. Then again we have here, we have this. Let's use another example. Ketone. It's a ketone, we call it butanone. Butanone. So in presence of hydrogen produced from zinc, mercury amalgam, and HCl, shall form our alkane. Form our alkane plus what? Plus water. Plus water. Yeah. So it replaces these two hydrogen atoms with replaces these two bonds. I don't know why I'm saying hydrogen. These two bonds with the hydrogen. So the remaining will form water. The oxygen will combine with the hydrogens here to form what? Water. So this is another method of preparation of alkanes in the laboratory. So as we said, these alkanes can also be found naturally from crude oil. When we look at the methods of separation of crude oil into different components, we shall see that alkanes can be also obtained from crude what? Oil. Yeah. So today, let's continue and talk about today's lessons. It's very small somehow. We're going to discuss about the physical properties of what? Alkanes. Yeah. So we're going to say that alkanes, naturally, they exist as gases, solids, and liquids, depending on their size. So we are going to say that the first 4 members are gases. The next from 5 up to C19 are what? Liquids, and the rest are what? Solids. So we have, let me illustrate for you. Now we are talking about physical properties. Physical properties of what? Of alkanes. So the first one is we look at their nature or physical state. So the first member, from C1 up to C4. From C1 up to C4, there are gases. Why are they gases? Because they have few intermolecular forces of interaction. Or we can say that these alkanes, because they are not polar, they are non-polar, they are bonded together with van der Waals forces. So you observe that the intermolecular force between, for example, methane and the methane is very weak, and hence it exists as a what? A gas. Then from C5 up to C19, there are liquids. So as the intermolecular forces increase, that is CH3, let's take CH3, CH2, 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 so we have 1, 2, 3, 4, 5. As the intermolecular forces increase, as they what? Increase. So they will hold these ones as what? Liquids, meaning the more the intermolecular forces, the more the compound will change physical what? State. Then from C5 from greater than C19, we shall have what? Solids, because they have more intermolecular forces to hold them as what? Solids. This comparison can be compared to when we have group 7 elements. Group what? 7 what? Elements. So we say the physical states will change depending on their size. Like fluorine is naturally a gas because it is very small with few intermolecular forces, then exists as a gas. Then we have, for example, chlorine. Intermolecular forces are few, then exists as a what? A gas. Then we have bromine. Intermolecular forces are few, but for it they are more, and then it exists as a what? A liquid, you see? Then iodine, solid, exists as a what? A solid. So you see how the physical states change as size becomes big. Even here, as size become big, then the physical states will also change. So this is how these organic compounds look like depending on their sizes. Then we have another factor here, which we are going to call a boiling point. Boiling what? Point. Boiling point and the melting what? Points. Yeah. So let's look at our slides. So we are going to see that actually the boiling points and the melting points of alkanes increase with increase in molecular mass, because as molecular mass size increases, there is increase in van der Waals forces of what? Attraction. There is increase in van der Waals forces of what? Attraction. So you recognize that as size become bigger, the van der Waals forces also become many. As they become many, then boiling points will increase. So we have the same illustration here, but I can explain it more here. Like, let's take an example again of methane. Few intermolecular forces. Just imagine it is one. So easy to break. Then, because it is easy to break, we say low boiling point. Or melting what? Point. Despite the fact this is already a gas, but the boiling point again will be low and it will be negatives. Then if we have, for example, pentane, any what? Pentane, this one. You see? We have 1, 2, 3, 4, 5. So it will have more intermolecular forces. More intermolecular forces. And the more the intermolecular forces, the more difficult is it to break this bond. So the more difficult it is to break this bond, the higher. We say we have high. High what? Boiling point. So we have higher boiling points when we have increase. Why do we say we have higher boiling points when we have bigger size? Because the van der Waals forces are many. If we use our illustration here, it may not be exactly as it is. You see that here we have 1 van der Waals force. Then here we have 1, 2, 3, 4, 5. So you observe that the energy required to break this one will be so little, so hence low boiling point. The energy required to break this 5 will be higher. It will be what? Higher. And because it is higher, then you have a high boiling what? Point. So as mass B increases, especially here when we have solids, when we have what? Solids. As mass increases, then we shall have increase in boiling point. Then NB, we are going to note that, however, the boiling points decrease with increase in branching. Increase in what? In the branching. So the more the branching, the higher the boiling what? Points. You look at your slides and see we have an example here. An example. When we have a straight chain, when you have a straight what? Chain. When you have a straight chain, you will see it has 36. It has what? 36. When we have one branch, it is 28. Then the more the branches, the lower the boiling what? Point. So it means as the boiling point as the branching is increasing, the lower the boiling what? Point. Someone may ask why? Why? So we have tried to give the explanation here. So because as branching increases, the surface area of interaction, or we can say of attraction, decreases, which leads to decrease in intermolecular forces of attraction, hence decrease in boiling what? Point. Let me illustrate to you on the blackboard here, where we have here, when we have straight chain, for example, this one, we are going to use pentane again, pentane. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So you observe this is a straight chain to have more intermolecular forces. More intermolecular forces. But if you have a branch, if you have a what? A branch. This is our branch here. The branched chain. You have a branched what? Chain. Branched chain. So the more the branching, so you see this one has more branches compared to this one. So this branching will decrease the surface area for formation of intermolecular forces. So like for example, we are trying to show it like using our blackboard. So if again we compare with the number of van der Waals forces, you see this one will form more van der Waals forces. That's why we have said in our explanation, because as branching increases, the surface area of attraction, of formation of van der Waals forces, of formation of intermolecular forces decreases. So here we have less surface area. This one has more surface area, which leads to decrease in the intermolecular forces of attraction. So we have few. Like here, if you are counting, we will say 3. Few van der Waals what? Forces. Then here we have what? 5. So the more the van der Waals forces, then we shall say we are having a higher what? Boiling point. Like this one we have said is 36 degrees, and here is what? 10. Yet they have the same number of carbon atoms and the same molecular mass. So that's why we say, so whenever we have more branches, we shall have low boiling what? Point. Low boiling point. So let's look at our slides and then we talk about another point. Another what? Points. So we are going to say that alkanes are insoluble in water because they are nonpolar. They are nonpolar. So if you remember very well, we try to explain the reason why we have the tetrahedral structure forming nonpolar, despite the fact that sometimes it has polar bonds. We said because of equal pool of bonding electrons in all directions, which cancels out the effect of what? Polarity. So, however, they are soluble in organic solvents, and they are themselves good organic what? Solvents. So, they are nonpolar because water is polar. They don't dissolve normally. This is why you observe that when you have, for example, fuels, that is petrol, paraffin, they are insoluble in water. Why? Because of that non-polar characteristic. Then, when you dissolve them in organic solvents, they are soluble. They are also organic solvents. So one of the uses and the applications of these alkanes is them being good organic solvents. Good organic solvents. So, there's another thing we normally talk about when we talk about solubility. We normally say like dissolves like. Like dissolves like. Like that English proverb which says birds of the same feathers move together. We can relate it to that. So you observe that when something is polar, it will dissolve polar. So water molecules normally dissolve those compounds which are polar because of the interaction between the polar bonds of water or the attraction. Then organic solvents will dissolve themselves because of the carbon atoms. Carbon what? Atoms. So that is our solubility. So we have talked about our physical properties. We can quickly pass through them. The first one was nature, and we saw that the first 4 are gases, and they are gases, and because they are gases, actually we use them as what we call, use them as when we apply them for cooking as our sources of, as our fuel, Actually, we shall call them the natural what? Gases. Then C5 and up to C19, they are liquids, and that is, we also apply them as fuels, like for example in petrol, in diesel. As you know, these things are also, they are also what? They are also liquids. They are also what? Liquids. Then greater than that, they are normally solids. So then the boiling points, we say they increase with increase in size due to increase in the van der Waals forces of what? Van der Waals forces of interaction. Then we said, but you should note that as branching increases, the boiling points also decrease. Then finally, we talk about the solubility. Alkanes are insoluble in water because they are non-polar, and they are soluble in organic solvents because they are also good organic solvents, and because like dissolves like. Then we are going to now make an illustration. So we have a question there. We are going to say, write down the possible isomers of C8H18 and name them. Choose the isomer that has the lowest boiling point, that has the highest boiling what? Point. So we are going to try to write down these isomers together. We are going to write as many as possible. As many as what? Possible. So when you're writing isomers, it is good for us to know that we normally begin with our straight chain isomers. So we may not name, but you guys will name for us, or you will give names. So we have here, this is our first isomer. We have 1, 2, 3, 4, 5, 6, 7, 8 straight chain. Then we have one which has one branch. So we can put a branch here. Have a branch. And put a branch. We have 1, 2, 3, 4, 5, 6, 7, 8. We can put another one with another branch. Hope you are learning something and you are enjoying our lesson. So we are making another isomer. Another what? Isomer with one branch. So we have 1, 2, 3, 4, 5, 6, and 7. Let's check this one. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8. So we have 1, 2, 3, 4. So we can also put another isomer here. Another what? Isomer. So we have, these are all different isomers with one what? And branch. So we say 1, 2, 3, 4, 5, 6, 7, 8. So we can create other isomers which have two branches. Which have what? Two branches. Like for example, let me put on carbon number 3. So we can do like this. Carbon number 3, CH2. CH2. So we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. So we can also put on carbon number 2 with the 2 what? Alkali groups. So 1, 2, 3, 4, 5, 6, 7, 8. So we can, if we put here, it will be the same as the other one. So we can also separate these ones. We put here CH3 here and also CH3 there. Oh, we can create as many isomers as possible. As many isomers as what? Possible. So we have 1, 2, 3, 4, 5, 6, 7, 8. The list is very long. This is very what? Long. So these are our isomers. Hope you can give them names. Can give them what? Names. We can also write the last one, which has very many, very many. CH2. Then we can put another one. So we say 1, 2, 3, 4, 5, 6, 7, 8. Hey, there are many. So the students will name for us these isomers. They choose the isomer which has the highest boiling point, the lowest boiling point, and the form optical what? Isomers. Form optical what? Isomers. Forms optical isomers. So the students should look at those isomers. They should look at those isomers. They name them. Choose the isomer which forms the lowest boiling point, the one which has the highest boiling point, and forms optical what? Isomers. The one which has the highest boiling point should be the one which is straight, as we have seen. The one which has the lowest boiling point should be the one which has more branches. The one which forms optical isomers, you should be able to choose. The one which has a chiro carbon. So you can even add on the list as long as what? As possible. So make sure you try it out. So we have also another homework. Using the equations, explain 4 methods of preparation of what? Of alkanes. You try it out also. Thank you very much for following me today. Hope you've learned something about the physical properties of alkanes and the uses of alkanes. I can give you a simple question. If you can give me 2 uses of alkanes from what we have spoken about, God bless you very much. We shall meet next time.